For all of human history, the edge of our solar system was a fixed, visible wall. If you looked up into the night sky, Saturn was the absolute limit. Beyond its orbit lay an incomprehensible void, forming the unbreakable boundary of the known universe. That boundary shattered in 1781. Using a homemade reflecting telescope in his English garden, astronomer William Herschel spotted a faint, slow-moving object. Mathematical analysis quickly confirmed it wasn't a comet, but a massive primary planet. In a single stroke, humanity doubled the known size of the solar system. Eventually, the German astronomer Johann Bode proposed a compromise rooted in mythology. Since Saturn was the father of Jupiter, this new planet should take the name of Saturn's father, the Greek sky deity, Uranus. This side-by-side diagram illustrates why Uranus required a totally new scientific classification. For decades, it was lumped in with Jupiter and Saturn as a gas giant. But unlike those planets, which are overwhelmingly composed of hydrogen and helium, Uranus is packed with heavier substances. It holds massive quantities of water, ammonia, and methane, materials that astronomers classify as ices. This required the invention of an entirely new planetary category, the ice giant. Uranus proved the solar system didn't simply fade out into emptiness. It revealed a deep outer zone governed by different chemical rules, forcing scientists to rethink how planets accrete and form in the darkest, coldest regions of space. While most planets spin like tops, Uranus has an extreme axial tilt of 97.77 degrees, orbiting like a rolling ball. A massive collision may have knocked it over, or gravitational resonance from a migrating Planet 9 gradually pulled its axis sideways. Because of this tilt, Uranus experiences the most extreme seasonal cycles of any known planet. It takes 84 Earth years to complete a single orbit. For 21 years, one pole points directly at the sun, basking in continuous daylight, while the opposite hemisphere plunges into decades of absolute freezing darkness. Despite decades of uninterrupted sunlight on its poles, Uranus is mysteriously cold. It holds the record for the coldest planetary atmosphere we've ever measured, dropping to -371 degrees Fahrenheit. Other giants, like Jupiter and Neptune, radiate massive amounts of internal heat to supplement the faint solar energy they receive. Uranus emits barely any. A planet with almost no internal heat flow should have a dead, stagnant atmosphere, yet observations reveal incredibly violent weather. Massive zonal winds tear across the planet at up to 560 miles per hour, with equatorial storms blowing opposite the planet's rotation. Meanwhile, storms near the poles blow forward. The massive energy required to drive these supersonic winds has to come from somewhere. Without a strong internal heat engine, the external dynamics of Uranus completely defy the thermodynamic models that neatly explain the weather on every other giant planet. To understand why Uranus is so cold, we must look beneath the clouds. The planet lacks a true solid surface. Instead, the crushing depths of the mantle compress water, ammonia, and methane into a dense, churning supercritical fluid, a state blurring liquid and gas. Down here, pressures reach 8 million times that of Earth's atmosphere, and temperatures spike to 9,000 degrees Fahrenheit. The conditions are so extreme that methane molecules are physically crushed apart. The carbon atoms separate out and crystallize, creating a continuous hail of solid nanodiamonds sinking through the fluid mantle toward the rocky core. Deep inside, intense pressures create super-ionic carbon hydride. Carbon atoms freeze into a rigid hexagonal lattice. Meanwhile, hydrogen ions flow freely through this solid framework along spiral pathways. This highly directional flow of electrically charged particles dictates how heat and electricity move. The internal architecture of Uranus operates as a planet-sized chemical laboratory, driven by states of matter that force us to rewrite basic chemistry. The chaos inside the planet extends directly to the space surrounding it. While Saturn features broad, highly reflective dams of ice, the 13 rings of Uranus are surprisingly narrow and incredibly dark, composed of irradiated organic compounds. These particles are held tightly in place by the gravitational nudges of tiny shepherd moons. Beyond the rings orbit 28 known moons, famously named after characters from Shakespeare and Pope. The most fascinating is the small ice moon Miranda. Its surface is aggressively scarred by giant concentric fractures and massive fault cliffs up to 12 miles high. Geological models suggest Miranda may have been physically shattered by a massive impact and then reassembled by its own gravity multiple times. Uranus's magnetic field generates thousands of miles off-center and tilts 59 degrees. As the sideways planet rotates, this field whips around chaotically. The magnetosphere effectively flickers, opening to the solar wind and slamming shut every 17 hours. From its shattered satellite system down to its flickering, lopsided magnetic shield, the entire Uranian system bears the signature of profound, violent disruption. We know these anomalies exist, but our data is severely limited. Our direct understanding of this planet is derived almost entirely from a single 5-hour flyby executed by the Voyager 2 spacecraft in January 1986. We caught a brief, fleeting snapshot of the southern hemisphere and haven't been back since. To fill those massive gaps in our data, the National Academies of Sciences has prioritized a new flagship mission, the Uranus Orbiter and Probe. This mission would insert a spacecraft into a multi-year tour of the system and drop a dedicated probe directly through the freezing cloud layers. By measuring noble gases and isotopes directly, the sheer distance has always been the primary obstacle, with traditional rockets requiring over 13 years to make the trip. But next-generation heavy-lift architectures, like the SpaceX Starship, could launch massive scientific payloads on high-energy trajectories, cutting the transit time down to just 6 years.